At that moment, 3I Atlas passed close to Mars. Something changed. While most Earth-based telescopes tracked the comet, China's Tianwen-1 glanced outward and detected an abrupt shift in color. The familiar white, then yellow, then greenish glow had nearly disappeared, replaced by a deep, pulsating red. From its core, a heat signature unlike any comet radiated. That single observation might be the first evidence that 3I Atlas is more than a comet. It was awakening, and the world hadn't noticed. Tianwen-1's unexpected discovery. Tianwen-1 wasn't designed to hunt interstellar objects. Its instruments were intended to map Mars' surface, atmosphere, and climate patterns. Yet, in early October, as 3I Atlas approached Martian orbit, mission controllers quietly redirected one camera to scan the sky beyond the planet. The result was astonishing, a color transformation unseen by telescopes on Earth. In that brief window, the instrument captured 3I Atlas glowing crimson, where it had previously reflected sunlight as pale white, shifting through yellow and green in earlier observations. The comet now emitted a deep red light. The color wasn't uniform. It pulsed, fluctuating in intensity with a slow rhythm. The change was far too distinct to be a sensor error. Teams comparing the frame to Earth-based spectral readings detected matching infrared excesses, though those observatories had only noted faint anomalies, hints, not clarity. The red core, captured in high resolution by Tianwen-1 spectrometer, suggested the object was no longer passively warming or reflecting light. It had begun producing heat from within. The red emission lines aligned with ionized carbon and metallic vapors rather than organic fluorescence or scattered dust. Essentially, it resembled a reactor glowing from inside. This single image altered the narrative. What had once seemed a distant, curious comet now behaved like a machine. If 3I Atlas was self-activating, Tianwen-1 might have captured its first ignition. The question remained, was this red glow unique, or had it always existed, hidden until someone observed it closely from Mars? Spectral surge and thermal output. The data from Tianwen-1's infrared spectrometer stunned operators. Beijing Aerospace Flight Control expected the usual faint cometary signature, gentle peaks from frozen water, dust, and residual carbon dioxide. Instead, the graph erupted with sharp spikes across multiple wavelengths, indicating rapid internal heating. Surface temperatures exceeded 5,000 degrees Celsius, 10 times higher than a comet should reach at Mars' distance from the Sun. Initially, engineers suspected calibration errors, but repeated checks confirmed the anomaly. The thermal spikes recurred every 9 hours, perfectly matching 3I Atlas rotation cycle. The heat wasn't random. It pulsed from within, phased like a power output ramping. Ground-based infrared observations from the Atacama Desert confirmed rising CO2 emissions at 4.26 microns, consistent with engineered plasma exhausts. Scientists were disturbed not just by the emissions, but by their coherence. Unlike natural thermal radiation, which spreads broadly, these emissions were narrow, sharply defined, and steady. Tianwen-1's visual imager added another layer. The comet's halo shifted color almost frame by frame during heat surges, green fading into amber, then solid crimson. Algorithms filtering solar reflections could not account for this. It appeared as if the object was executing a controlled thermal sequence. The nickel signature and engine hypothesis. Once the full dataset from Tianwen-1 was decoded, the shock wasn't in the color, it was in the chemistry. Infrared spectra revealed nickel vapor lines, produced only when metal surpasses 3,000 degrees Celsius. No natural comet could vaporize nickel so far from the Sun, particularly near Mars' orbit. Repeated spectrometer checks confirmed the presence of ionized nickel gas. For planetary scientists, the implication was clear: metallic material inside 3I Atlas was burning. But how? Solar heating alone couldn't explain it. The release was rhythmic and controlled, almost mechanical. In propulsion engineering, nickel alloys endure extreme heat in plasma and ion engines. Their exhaust contains trace nickel vapor mixed with CO2, precisely what Tianwen-1 observed. Ratios between nickel, CO2, and dust mirrored human-made thrusters tested on early Mars orbiters. This prompted debate across China's aerospace community. Was 3I Atlas expelling exhaust? Or was it regulating energy internally? A thermal management system controlling power? Whatever the purpose, the readings marked a line no comet had crossed. Deliberate, active metal vaporization in space. Tianwen-1 had captured something generating heat, not just surviving it. Pulse pattern and self-regulation. Comparing thermal curves to time-stamped imagery revealed a strange order. Each heat surge coincided with a faint flicker in the red glow, a heartbeat repeating with machine-like precision. Over 12 rotations, the interval never varied. 9 hours for minutes, 32 seconds. To the Tianwen-1 team, this was beyond coincidence. Natural comets erupt randomly. 3I Atlas followed a schedule. Intensity ramped up, plateaued, then declined symmetrically, resembling a power cycle. Frequency analysis revealed harmonic overtones, mirroring controlled plasma oscillations. Even the magnetometer detected faint, synchronized magnetic disturbances. 3I Atlas wasn't just hot. It was electromagnetically active, defeating effect and rising mass. Beyond Mars, observatories tracked subtle mass shifts. Unlike normal comets, which lose mass near the Sun, 3I Atlas appeared to gain weight. Estimates rose from 10 billion tons to over 30 billion tons. Radar echoes confirmed the density increase. Its gravity attracted dust instead of repelling it. Spectral analysis showed charged silicates and magnetized grains spiraling into the nucleus. Chinese physicists proposed a radical hypothesis. The object was harvesting material, generating a localized magnetic field to pull interplanetary dust, compressing it, possibly converting it into energy. The magnetic envelope. Tianwen-1 detected faint, rhythmic oscillations in its communications band coinciding with a 9-hour cycle, unrelated to solar activity. The pulse originated from 3I Atlas itself, suggesting a magnetic envelope, a stable, structured field extending thousands of kilometers, modulated by an internal dynamo. It might shield the object from solar radiation, trap charged dust, or both. The Chinese data leak. For 2 weeks, the data remained secret. Then, a 14-megabyte file appeared online, tagged Tianwen-1. The image, October 14, 2025, 3:02 Universal Time Coordinated, showed a red sphere with concentric rings, a second smaller object tethered by a faint filament, labeled Frame 119 Internal Activation. Within hours, the leak spread globally. Observers verified the coordinates matched 3I Atlas orbit. NASA declined comment. The Chinese Academy of Sciences called it a fabrication. Yet the raw spectral data confirmed CO2 and nickel readings, and a 22-second EM feedback signal suggested the comet was responding. The second activation near Jupiter. By late November, 3I Atlas entered Jupiter's gravitational sphere. Instead of breaking apart, it brightened. Within 1 9-hour rotation, the red glow spiked tenfold. Infrared surges exceeded 50 gigawatts, while magnetized plasma streamed outward in directional exhaust-like channels. Its trajectory shifted precisely, velocity adjusted by 1.2 kilometers per second, enough to stabilize against Jupiter's pull. The implications were undeniable. This was no natural comet. The final phase and global silence. By December 12th, observatories reported 3I Atlas red radiance had vanished, returning to a faint white glow. Trajectory data revealed active deceleration. Velocity dropped nearly 2% relative to Jupiter. Tianwen-1 captured a fading broadband signal echoing the 9-hour activation cycle, spectrograms revealing fractal-like nested bands. 2 hours later, the transmission ceased. The comet blended into starlight. NASA, ESA, and CNSA released identical statements. 3I Atlas had passed beyond observation. Leaked internal summaries noted stabilization, a haunting confirmation. The object hadn't died. It had reached equilibrium. Somewhere beyond Jupiter, a one-sunlit object had learned to generate its own energy and then shut it off by choice. Tianwen-1's observation was unprecedented. The Chinese orbiter had not been designed for interstellar reconnaissance. Its instruments were focused on Mars' surface, atmosphere, and seasonal variations. Yet, in early October, mission controllers quietly repurposed one camera to monitor the sky beyond the planet, a decision that would change the way humanity understood this object. In a single, brief observational window, the instrument captured 3I Atlas glowing crimson, a stark deviation from the pale white, yellow, and green shades seen from Earth. The comet's color now suggested internal energy production, a deep red pulse that no telescope on Earth had resolved. The crimson glow was not uniform. It oscillated, pulsing in a steady rhythm that hinted at mechanical or energetic regulation. Initial comparisons with ground-based infrared readings suggested correlation, although those observatories had previously detected only vague anomalies, subtle hints of something unusual. Tianwen-1, however, resolved the details. The high-resolution spectrometer revealed that the object was generating heat from within, not merely reflecting sunlight. Red emission lines aligned with ionized carbon and metallic vapors, entirely inconsistent with natural cometary dust or organic fluorescence. For scientists, the image resembled a reactor core glowing from the inside, a living furnace in the void. This single frame forced a radical reevaluation. 3I Atlas, long cataloged as a distant comet, now exhibited behavior consistent with a machine capable of producing its own energy. If it was indeed self-activating, Tianwen-1 had documented the event in real time, perhaps witnessing the object's first recorded ignition. The essential question became clear. Was this internal activity unique to this observation, or had it been occurring undetected for eons, visible only when the right instruments observed from close range? Spectral surges and thermal readings shocked analysts. When raw telemetry from the infrared spectrometer arrived at Beijing Aerospace Flight Control, engineers expected the familiar, faint scatter of a cooling comet, minor peaks from frozen water, dust, and residual carbon dioxide. Instead, the data exploded across multiple wavelengths with jagged spikes, indicating rapid internal heating far exceeding any natural expectation. Surface temperatures were measured above 5,000 degrees Celsius, nearly 10 times higher than a comet should achieve at Mars' distance from the Sun. Repeated calibrations ruled out instrumental error. The anomaly persisted with startling precision. Each spike recurred every 9 hours, coinciding perfectly with the comet's known rotation. The heat was not random. It pulsed methodically, in a phased rhythm reminiscent of energy modulation in engineered systems. Ground-based infrared observatories confirmed the findings. CO2 emission bands at 4.26 microns were rising sharply, consistent with engineered plasma exhausts rather than simple outgassing. What unnerved scientists was not only the intensity, but the coherence. Unlike natural thermal radiation, which disperses broadly, these emissions were narrow, sharply defined, and unwavering. Tianwen-1's visual imager revealed additional anomalies. During thermal surges, the comet's halo shifted colors almost frame by frame, cycling from green to amber to deep crimson. Standard models of solar reflection or passive dust gathering could not explain the observed sequence. The comet appeared to execute controlled thermal cycles independent of sunlight exposure. The nickel signature was even more startling. Infrared spectra revealed lines corresponding to nickel vapor, material that requires temperatures exceeding 3,000 degrees Celsius to vaporize. A natural comet at Mars orbit could not produce such heat. Repeated verification confirmed ionized nickel gas in every frame. Planetary scientists concluded that metallic material inside 3I Atlas was actively burning. But conventional mechanisms, solar radiation, outgassing, or ice sublimation, could not produce a stable, rhythmic thermal curve. The nickel emission was periodic, precisely vented, almost mechanical in its consistency. In the field of propulsion engineering, nickel alloys are widely used in plasma and ion engines due to their heat resistance. Their operation produces trace nickel vapor along with CO2, exactly what Tianwen-1 detected. The ratios of nickel, carbon dioxide, and silicate dust even matched early human-made thruster tests on Mars orbiters. Debate ignited among China's aerospace community. Was 3I Atlas actively expelling exhaust? Or was it regulating internal energy, using heat and metal vapor as a power management system? Whatever the case, the object had achieved something unprecedented: deliberate metal vaporization in deep space. Tianwen-1 had captured not survival, but the generation of heat, suggesting 3I Atlas had moved from passive reaction to active response. Pulse patterns reinforced the sense of intent. Thermal spikes corresponded perfectly with faint flickers of red light, forming a repeating heartbeat across 12 rotations. The timing was exact: 9 hours 4 minutes, 32 seconds. Natural comets erupt unpredictably. Jets form randomly as sunlight interacts with volatile pockets. 3I Atlas, however, operated on a schedule. The intensity rose smoothly, plateaued, then declined symmetrically, resembling a controlled power cycle. Frequency analysis revealed harmonic overtones, secondary peaks indicating regulated plasma oscillations. Tianwen-1's magnetometer even recorded faint magnetic disturbances synchronized with these pulses, further evidence of structured electromagnetic activity. 3I Atlas was not merely hot. It was responsive,